Section 4 of Familiar Letters on Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Peter Yearsley. Familiar Letters on Chemistry by Justus, Liebig. Letter 4. My dear Sir, one of the most influential causes of improvement in the social condition of mankind is that spirit of enterprise which induces men of capital to adopt and carry out suggestions for the improvement of machinery, the creation of new articles of commerce, or the cheaper production of those already in demand. And we cannot but admire the energy with which such men devote their talents, their time, and their wealth to realize the benefits of the discoveries and inventions of science. For even when these are expended upon objects wholly incapable of realization, nay, even when the idea which first gave the impulse proves in the end to be altogether impracticable or absurd, immediate good to the community generally ensues. Some useful and perhaps unlooked-for result flows directly or springs ultimately from exertions frustrated in their main design. Thus it is also in the pursuit of science. Theories lead to experiments and investigations, and he who investigates will scarcely ever fail of being rewarded by discoveries. It may be, indeed, the theory sought to be established is entirely unfounded in nature, but while searching in a right spirit for one thing, the inquirer may be rewarded by finding others far more valuable than those which he sought. At the present moment electromagnetism, as a moving power, is engaging great attention and study. Wonders are expected from its application to this purpose. According to the sanguine expectations of many persons, it will shortly be employed to put into motion every kind of machinery, and amongst other things it will be applied to impel the carriages of railroads, and this at so small a cost that expense will no longer be matter of consideration. England is to lose her superiority as a manufacturing country, inasmuch as her vast store of coals will no longer avail her as an economical source of motive power. We, say the German cultivators of this science, have cheap zinc, and how small a quantity of this metal is required to turn a lathe, and consequently to give motion to any kind of machinery. Such expectations may be very attractive, and yet they are altogether illusory. They will not bear the test of a few simple calculations, and these our friends have not troubled themselves to institute. With a simple flame of spirits of wine, under a proper vessel containing boiling water, a small carriage of 200 to 300 pounds weight can be put into motion, or a weight of 80 to 100 pounds may be raised to a height of 20 feet. The same effects may be produced by dissolving zinc in dilute sulphuric acid in a certain apparatus. This is certainly an astonishing and highly interesting discovery, but the question to be determined is, which of the two processes is the least expensive? In order to answer this question, and to judge correctly of the hopes entertained from this discovery, let me remind you of what chemists denominate equivalents. These are certain unalterable ratios of effects, which are proportionate to each other, and may therefore be expressed in numbers. Thus, if we require 8 pounds of oxygen to produce a certain effect, and we wish to employ chlorine for the same effect, we must employ neither more nor less than 35½ pounds weight. In the same manner 6 pounds weight of coal are equivalent to 32 pounds weight of zinc. The numbers representing chemical equivalents express very general ratios of effects, comprehending for all bodies all the actions they are capable of producing. If zinc be combined in a certain manner with another metal, and submitted to the action of dilute sulphuric acid, it is dissolved in the form of an oxide. It is in fact burned at the expense of the oxygen contained in the fluid. A consequence of this action is the production of an electric current, which if conducted through a wire renders it magnetic. In thus effecting the solution of a pound weight, for example, of zinc, we obtain a definite amount of force, adequate to raise a given weight 1 inch. and to keep it suspended, and the amount of weight it will be capable of suspending will be the greater the more rapidly the zinc is dissolved. By alternately interrupting and renewing the contact of the zinc with the acid, and by very simple mechanical arrangements, we can give to the iron an upward and downward or horizontal motion, thus producing the conditions essential to the motion of any machinery. This moving force is produced by the oxidation of the zinc, and setting aside the name given to the force in this case, we know that it can be produced in another manner. If we burn the zinc under the boiler of a steam engine, consequently in the oxygen of the air instead of the galvanic pile, we should produce steam, and by it a certain amount of force. If we should assume, which however is not proved, that the quantity of force is unequal in these cases, that for instance we had obtained double or triple the amount in the galvanic pile, or that in this mode of generating force less loss is sustained, we must still recollect the equivalents of zinc and coal, and make these elements of our calculation. According to the experiments of Despretz, 6 pounds weight of zinc, in combining with oxygen, develops no more heat than 1 pound of coal. Consequently, under equal conditions, we can produce 6 times the amount of force with a pound of coal as with a pound of zinc. It is therefore obvious that it would be more advantageous to employ coal instead of zinc, even if the latter produced 4 times as much force in a galvanic pile as an equal weight of coal by its combustion under a boiler. Indeed, it is highly probable that if we burn under the boiler of a steam engine the quantity of coal required for smelting the zinc from its ores, we shall produce far more force than the whole of the zinc so obtained could originate in any form of apparatus whatever. Heat, electricity, and magnetism have a similar relation to each other as the chemical equivalents of coal, zinc, and oxygen. By a certain measure of electricity we produce a corresponding proportion of heat or of magnetic power. We obtain that electricity by chemical affinity, which in one shape produces heat, in another electricity or magnetism. A certain amount of affinity produces an equivalent of electricity, in the same manner as on the other hand we decompose equivalents of chemical compounds by a definite measure of electricity. The magnetic force of the pile is therefore limited to the extent of the chemical affinity, and in the case before us is obtained by the combination of the zinc and sulphuric acid. In the combustion of coal the heat results from, and is measured by, the affinity of the oxygen of the atmosphere for that substance. It is true that with a very small expense of zinc we can make an iron wire a magnet capable of sustaining 1,000 pounds weight of iron. Let us not allow ourselves to be misled by this. Such a magnet could not raise a single pound weight of iron 2 inches, and therefore could not impart motion. The magnet acts like a rock, which while at rest presses with a weight of 1,000 pounds upon a basis. It is like an enclosed lake, without an outlet and without a fall. But it may be said we have, by mechanical arrangements, given it an outlet and a fall. True, and this must be regarded as a great triumph of mechanics, and I believe it is susceptible of further improvements, by which greater force may be obtained. But with every conceivable advantage of mechanism, no one will dispute that 1 pound of coal, under the boiler of a steam engine, will give motion to a mass several hundred times greater than a pound of zinc in the galvanic pile. Our experience of the employment of electromagnetism as a motory power is, however, too recent to enable us to foresee the ultimate results of contrivances to apply it, and therefore those who have devoted themselves to solve the problem of its application should not be discouraged, inasmuch as it would undoubtedly be a most important achievement to supersede the steam engine, and thus escape the danger of railroads, even at double their expense. Professor Weber of Göttingen has thrown out a suggestion that if a contrivance could be devised to enable us to convert at will the wheels of the steam carriage into magnets, we should be enabled to ascend and descend acclivities with great facility. This notion may ultimately be to a certain extent realized. The employment of the galvanic pile as a motory power, however, must, like every other contrivance, depend upon the question of its relative economy. Probably some time hence it may so far succeed as to be adopted in certain favourable localities. It may stand in the same relation to steam power as the manufacture of beet sugar bears to that of cane, or as the production of gas from oils and resins to that from mineral coal. The history of beet root sugar affords us an excellent illustration of the effect of prices upon commercial productions. This branch of industry seems at length, as to its processes, to be perfected. The most beautiful white sugar is now manufactured from the beet root, in the place of the treacle-like sugar, having the taste of the root, which was first obtained, and instead of 3 or 4%, the proportion obtained by a card, double or even treble that amount is now produced, and, notwithstanding the perfection of the manufacture, it is probable it will ere long be in most places entirely discontinued. In the years 1824 to 1827 the prices of agricultural produce were much lower than at present, while the price of sugar was the same. At that time 1 malter of wheat was 10 shillings, and 1 klafter of wood 18 shillings, and land was falling in price. Reader's note: a malter was a measure containing several bushels, but varying in different countries, and a klafter was a cord, a stack, measuring 6 feet every way. End note. Thus food and fuel were cheap, and the demand for sugar unlimited. It was therefore advantageous to grow beet root, and to dispose of the produce of land as sugar. All these circumstances are now different. A malter of wheat costs 18 shillings, a klafter of wood 30 shillings to 36 shillings. Wages have risen, but not in proportion, while the price of colonial sugar has fallen. Within the limits of the German Commercial League, as for instance at Frankfurt on the Main, a pound of the whitest and best loaf sugar is 7d. The import duty is 3d halfpenny, or 30 shillings per hundredweight, leaving 3d halfpenny as the price of the sugar. In the year 1827, then, 1 malter of wheat was equal to 40 pounds weight of sugar, whilst at present that quantity of wheat is worth 70 pounds of sugar. If indeed fuel were the same in price as formerly, and 70 pounds of sugar could be obtained from the same quantity of the root as then yielded 40 pounds, it might still be advantageously produced; but the amount, if now obtained by the most approved methods of extraction, falls far short of this; and as fuel is double the price, and labour dearer, it follows that at present it is far more advantageous to cultivate wheat and to purchase sugar. There are, however, other elements which must enter into our calculations, but these serve to confirm our conclusion that the manufacture of beet root sugar, as a commercial speculation, must cease. The leaves and residue of the root, after the juice was expressed, were used as food for cattle, and their value naturally increased with the price of grain. By the process formerly pursued, 75 pounds weight of juice were obtained from 100 pounds of beet root, and gave 5 pounds of sugar. The method of Schutzenbach, which was eagerly adopted by the manufacturers, produced from the same quantity of root 8 pounds of sugar, but it was attended with more expense to produce, and the loss of the residue as food for cattle. The increased expense in this process arises from the larger quantity of fuel required to evaporate the water, for instead of merely evaporating the juice, the dry residue is treated with water, and we require fuel sufficient to evaporate 106 pounds of fluid instead of 75 pounds, and the residue is only fit for manure. The additional 3 pounds of sugar are purchased at the expense of much fuel and the loss of the residue as an article of food. If the valley of the Rhine possessed mines of diamonds as rich as those of Golconda, Visiapur, or the Brazils, they would probably not be worth the working. At those places the cost of extraction is 28 shillings to 30 shillings the carat. With us it amounts to 3 or 4 times as much, to more in fact than diamonds are worth in the market. The sand of the Rhine contains gold, and in the Grand Duchy of Baden many persons are occupied in gold washing when wages are low, but as soon as they rise this employment ceases. The manufacture of sugar from beet root in the like manner 12 to 14 years ago offered advantages which are now lost. Instead, therefore, of maintaining it at a great sacrifice, it would be more reasonable, more in accordance with true natural economy, to cultivate other and more valuable productions, and with them purchase sugar. Not only would the state be the gainer, but every member of the community. This argument does not apply perhaps to France and Bohemia, where the prices of fuel and of colonial sugar are very different to those in Germany. The manufacture of gas for lighting from coal, resin, and oils stands with us on the same barren ground. The price of the materials from which gas is manufactured in England bears a direct proportion to the price of corn. There the cost of tallow and oil is twice as great as in Germany, but iron and coal are 2/3 cheaper. And even in England the manufacture of gas is only advantageous when the other products of the distillation of coal, the coke, etc., can be sold. It would certainly be esteemed one of the greatest discoveries of the age if anyone could succeed in condensing coal gas into a white, dry, solid, odourless substance, portable and capable of being placed upon a candlestick or burned in a lamp. Wax, tallow, and oil are combustible gases in a solid or fluid form, which offer many advantages for lighting not possessed by gas. They furnish, in well-constructed lamps, as much light, without requiring the expensive apparatus necessary for the combustion of gas, and they are generally more economical. In large towns, or such establishments as hotels, where coke is in demand, and where losses in stolen tallow or oil must be considered, together with the labour of snuffing candles and cleaning lamps, the higher price of gas is compensated. In places where gas can be manufactured from resin, oil of turpentine, and other cheap oils, as at Frankfurt, this is advantageous so long as it is pursued on small scale only. If large towns were lighted in the same manner, the materials would rise in price. The whole amount at present produced would scarcely suffice for 2 such towns as Berlin and Munich. But no just calculation can be made from the present prices of turpentine, resin, etc., which are not produced upon any large scale. End of section 4.